Good morning, everybody. Welcome to this PSE Dean's Distinguished Seminar by Professor Pratim Biswas. Professor Biswas is currently the Dean of Engineering and also Professor in Chemical Engineering, Chemical, Environmental, and Materials Engineering and Atmospheric Sciences at the University of Miami. I have known Pratim for almost over 30 years. So we joined the same research group at Caltech, but I think he left a year before I joined, but afterwards I met him in meetings, in Aerosol meetings, etc. So very good to have you here, Pratim. So prior to joining the University of Miami, he was the Lucy and Stanley Lupita Professor and Chair of the Department of Energy, Environmental, and Chemical Engineering, as well as Assistant Vice Chancellor for International Programs at Washington University in St. Louis. So as mentioned, Professor Biswas received his PhD from Caltech, Master from UCLA, and Bachelor degrees from IIT Bombay. His research and education interests focus on aerosol science and engineering with applications in nanoparticle technology, air quality, environmentally benign energy production, combustion, material processes, etc. He has developed the world-renowned aerosol and air quality research laboratory. He has graduated 65 PhDs and published close to 500 journal papers. He has received a number of awards in the chemical engineering and aerosol community, and also he was elected to the National Academy of Engineering in 2019. He has 2 startups in the area of aerosol science and technology and nanoparticle technology. So he will talk about aerosol science and technology, enabling synthesis of advanced materials to promote circular economies. Please join me in welcoming Professor Biswas.
Thank you, Chuck, for that nice and kind introduction. Today you'll hear about aerosol science and technology, and I'll of course give a broader overview, but then begin to narrow down and also illustrate the number of different things that can be done. The title has this word circular economy. I noticed, I think there's a workshop going on. That's just coincidental. And I will just refer to that maybe 2 or 3 times to illustrate the importance. This is a wonderful field, very specialized in some sense, but with large number of applications. It's great to be here, KAUST, and this is my first visit. And I met several of your faculty and colleagues here, and learned a lot about all the exciting work. So let's just go. Before I start, we should thank our students. I will in fact present some of their results, and also the funding agencies over the years and even currently supporting us, though now of course we are waiting for observing what happens to our federal agencies. But tremendous support over all these years. And my colleagues at the top, you will see I guess this pointer, okay. Top is CAST. We have a tremendous group of aerosol scientists, both in engineering and the Marine and Atmospheric Sciences School. And we all work together for a number of different areas. So University of Miami, it's in Florida, way out in the south. We are a member of the Association of American Universities. There are actually 71, but 69 are in the US. And there's a big emphasis on engineering in this association. So it's very good to be there. And I've recently moved, as Chuck mentioned, and we are building a very strong group of colleagues by recruiting a lot of different faculty. The university is comprehensive. There are 13 schools and colleges, 17,000 students. It's a private school. So in some sense, that's small compared to United States. In engineering, we have all 6 departments, and we go at it. So this, I thought, would just be one slide that I mention about the university. So I will talk about aerosols. Many of you might be experts, so please bear with me, but I'll try to sort of come up with this over-encompassing equation, which then is applied to so many different areas. I'll focus more on the physics, just to narrow it down, and also discuss some solution methodologies. And then once we have these tools, we can very successfully use them to design a whole set of processes. One, to of course understand particle behavior, but or aerosol behavior, but also to really synthesize materials. And that has been a big push. Folks may not call it aerosol processes, or they might refer to it as gas phase processes, sometimes spray processes, but we'll of course stick to our field and call it aerosol process. Then I'll pick carbon nanoparticles and try to illustrate some of the things I talked about. So aerosol, it's a Greek origin. It's just a suspension of particles in air. And again, very simple definition. It could be any solid or liquid particle. And a particle we define as a stable cluster of molecules or sometimes atoms, if it is elemental, like carbon. I just mentioned carbon. But these particles are suspended, and it is suspended in an ensemble of molecules, right? For example, we can't see many particles, but all of you are breathing and you're inhaling these particles, but along with that, you're also inhaling gases, vapors, and so forth. So an ensemble of molecules which are not clustered, and it's this relationship which we really need to understand as we move from one state to the other. Now, I could have molecules, for example, in this room of water vapor, and they could be unclustered, but if the conditions are right, they might cluster together and form little droplets or form little particles which are stable, and that is then referred to as an aerosol, okay? So I thought I'd just mention that, and with that comes all kinds of applications, but let's focus on the top, and I'm starting intentionally with molecules. You don't have to, because in this room I might have dust particles, and of course they're made up of molecules, they're a stable cluster of molecules, but I can start with individual molecules, and they can cluster together to form stable clusters or multi-component clusters. Then these clusters can collide and become larger, stick together, and eventually I have a multi-component aerosol. I might have it in a flow system. Another pathway is molecules can associate with the cluster, and that we refer to as condensation. But then the transport, capture, deposition gives me the ability to also make thin films, particles, powders, and so forth. These fundamentals are actually used. Climate and environment is extremely common, and a large group of researchers study that. The uncertainty with climate change due to particles is well understood or is well known or accepted, and the studies are underway to improve the understanding. We can use environment or health. As I said, we are inhaling it, and we just came off a pandemic, COVID, so the if these particles happen to be biological, they might cause infection and so forth. So they impact health. Then advanced materials, which I'll talk about today. Medicine, while we have adverse health effects, I can intentionally design drugs and inhale them and deposit them or introduce it into the body. Or I could make these nanomaterials, nanoparticles, and use it to target a tumor through a vascular transport system. Energy, like we can make thin films of photovoltaics. Agriculture, this is another global challenge issue we face. Can I improve the yield of our vegetation and so forth, fruits, vegetables? Can I use aerosol techniques to deliver nutrients very effectively? And finally, a lot of commodity powders are made by these techniques. And I won't go into all of them. And it's really a fascinating field. And different individuals or groups work with these different things and bring this together. So let's dive in a little more now. So I start with molecules, as I said. They could be different kinds. And these molecules are moving around. We are well aware of the kinetic theory of gases, which give it a certain speed depending on the temperature. But then they can collide if the conditions are right. As they collide, they might stick together and form these clusters, right? This process is really the birth of particles, and I'm referring it to this way because I'm intentionally going to want to make particles later on in the example that I choose. So the nucleation process, and these are all dynamic processes. There's a certain characteristic time, and I can, of course, define it as a certain critical concentration divided by a nucleation rate. I'm not going into too much detail, and I can show it on a plot of particle size with respect to time and so forth. The other process is collisional growth, and just to quickly go, condensational growth is a molecule then attaching to the cluster and forming eventually the multi-component aerosol. So condensational and collisional growth will have similarly characteristic times, and the equations become a little longer but not too complex because you can, of course, model the movement of these particles, in this case due to Brownian motion, or it could just be any collision mechanism which brings them together, and you can come up with a characteristic time. There is a concept of size, and you can see that I have two expressions, one in the continuum regime, and that is a comparison of particle size to the mean free path. So rather interesting physics that takes place here. And then, of course, if the particles are rather small, then they are in the free molecular regime. So they sort of act like a molecule itself, or somewhat like a molecule, and obviously there's a transition regime. Similarly, I can write an expression for the condensation characteristic time. Of course, there are many variables. I'm not pointing out each of them, but just to tell you that this is a dynamic process, and there is a concept of time that we'll have to deal with. And if I'm building a reactor or putting some practical application, we need to keep a sense of the times and compare them and so forth. Okay, so then I can show this. There are other mechanisms. Sintering is once I have collided my clusters, do they merge into a nice spherical shape and so forth. And I can cover multiple scales, starting with the molecular scale, of course, nano, meso, micro, even milli scale. So it's several orders of magnitude. The net to take from this is also, due to these processes, I'm going to get a distribution of particle sizes, right? And different concentrations. So the particle size might end up not being a single size, but a whole range of sizes and different concentrations that we really have to then account for. Okay, so I can take all of this and put it into a governing equation. Those who are chemical engineers, you might have heard of a population balance equation. So this is nothing but the population balance. I write down the size distribution function. The concentration is a function of size. Intentionally, I'm choosing volume as a metric of size, not the diameter. That makes it easier in some sense to define a volume if the particle is not spherical and so forth, right? And there is also composition. I haven't even talked about it. There could be the charge that the particles carry, which will also be function of size. So depending on the problem studied, I'll have many more parameters. But here I'll just say that n is a function of the particle size, in this case volume, and time, right? So the change in the size distribution function, there is a transport term, that's the first term. I'll tell you what that velocity term is, an expression for that. And on the right-hand side, a nucleation term. There is a critical size that which these clusters will form at. Below that critical size, they just break apart, and I don't form stable clusters. So that's the delta function, and then a nucleation rate, then a condensation rate, and a collision rate, which is an integral sort of equation, right? It is a summation of everything colliding with every possible size, resulting in growth. And when you also have a negative term because you lose a certain size of particles by collision with other particles and so forth. In terms of the transport, in dimensionless form, I can write down, it of course depends on the fluid velocity. Any engineered system, I'm going to have flow, I'm going to move things around, but then I have inertial effects represented by a Stokes number, diffusion, right? These small particles diffuse, so a Peclet number, then gravitational effects if the particles are large, Froude number, and then of course things like external force fields, thermophoresis, electrical force fields, and so forth, right? So this equation looks complex, but I really want to try and solve it. But let's see, how would one solve it? Let's say I want to solve in the range from 1 nanometer to 100 nanometer, rather small range. These particles could be in a whole spectrum of sizes. I will write down the volume below, and just assuming it to be spherical, use the relationship. So you see that it goes from 0.5 nanometer cube to about 500,000 nanometer cube. But I want to know the concentration at every particle size. The increment in the particle size is basically one molecular dimension, right? Because one molecule could add up to my smaller particle and become slightly larger, and so forth and so forth. So I keep track of the molecular volume, which is shown here, and just approximate numbers and assuming things to be spherical. And the reason we like volumes is also when two particles collide, I can just add up their volumes, so that volumes are additive, whereas diameters clearly are not, and there's no concern about the shape and things. So if I calculate the number of discrete sizes, it's rather straightforward, and you see I have to solve that equation for every size. There are about 10 to the 8 equations or 10 to the 9 equations, even in the small range that I'm interested in. So not easy, even with the fastest supercomputer and so forth. So all kinds of techniques are used. Then on top of it, I might want to know the orientation of the molecules. I want to know the composition. I might want to know the charge, and things are moving around, so it makes it even more complex, right? I'm not going into it. I've just listed some of the examples over the years that we look at, and then you want to bring in different theories, all kinds of things, and different techniques which are listed below. Eventually, being a good engineer, I want to apply it to a reactor, to maybe a drinking water distribution system, to a combustor, and so forth. But you can understand the complexity. So all kinds of simplifications are made. One, I'll assume every particle to be a single size at a given time. That's a simple monodisperse model. I can assume a shape, but there are discrete sectional models which are now being developed and reasonably accurate. I can use Monte Carlo techniques and so forth, right? So many different ways. Of course, everybody wants to delve into machine learning. This is a classic example for a big data system. Just see the number of terms. So there are folks now looking at neural network type models, and we ourselves want to integrate the physics-based neural network models and use them, and we have done that. I'll just illustrate that, and then we'll move on. So I can use this as a training data set. I can pick one of those accurate models, like the discrete sectional model, and the student will run this 60,000 times. I choose an initial distribution, run the sectional model for a certain time, get a final distribution, and keep running this and create a large data set. I could also go, we have tremendous tools now to measure size distributions. And remember, there's composition, there's all those other things I'm not even getting into at this stage. There are tremendous instruments that can generate data from reactors in an industrial setting, and that would give me additional data sets if needed. But here we do that, and then I can train it, very traditional neural network type model, and I get a series of layers and number of neurons per layer, and then hopefully given, so it's basically taking that integral differential equation and with a data-based approach, converting it to a matrix multiplication problem, right? So it's much faster. Is it accurate enough? Those are things to be, of course, resolved. But by training it then, given a certain input, given a certain time, I can then predict what the resultant size distribution would be, presuming if this works well. I want to bring in physics-based, both to improve the accuracy, and this is reality too. I understand the collisional growth process, so we might want to do that. We might want to further minimize computational time. So you see that there is a sort of loop based on, and you think about all those characteristic times that I said. I would do it for one characteristic time for coagulation, and then just crank out this, and then just do the comparison. The dots are the more accurate predictions. The log normal model sort of predicts, but then gives you a peak, whereas the network model is much better. You can look at the CPU time. You can play with these and then end up with tools that now I can use for a given reactor system or a given system, and I can bring in other aerosol dynamic phenomena, okay? So with that, let's say we have the tools, we have, and I'm again just focusing on the physics. I'm talking about the physics, but there's a chemistry involved, there's transport, deposition, and I want to now divert to functional nanomaterials. One, I can sit and do fundamental studies because these reactors allow me to produce particles with a certain size or a certain size distribution, and then I can measure the characteristics of particles, or I can jump into applications and so forth. So large number of researchers do this, including in industry. If you want to make a catalyst, you want to control the size, the shape, composition, crystal structure, people are doing this, and there are, of course, review papers already now. You also bring in online measurements, and our tools that we have for aerosol measurements are rather advanced because they give you a quantitative size distribution, not just a qualitative distribution, and then you want to verify your models and use them. So these are just some examples of reactors. This is a simple flame reactor. I like a high temperature environment because it's easy to go into the molecular state. I can react precursors and create those molecules that I need to produce my particles, right? I can, and of course there's a lot of control systems, measurement systems. I can also have an externally heated reactor, which is externally heated with the furnace, so we call it a furnace reactor. And then electrospray type reactors, where I don't elevate it, but I can produce tiny droplets with a certain charge. I can evaporate the droplets and study these very precisely. And things like for drug delivery and things like that, and even for some measurements, we can use these electrospray systems. Whole bunch of particles over the years. I won't even go through it, but and you can look at all kinds of applications which are outlined in these publications. And even our current work, all the way from perovskite materials, which are solar photovoltaic materials, to nanoparticle delivery drugs. We are synthesizing these, collaborating with other researchers and folks interested in application and doing all kinds of things. Okay, so functionality can be achieved, the understanding. A quick message is I can now produce a certain structure which has a certain functionality, certain size, composition, but is that enough, right? Do I need to go the next step? And I talked about this. They can be produced, but the concept of sustainability comes in because many of these materials are produced in large volumes, or eventually you want to produce it in large volumes, and then the concept of sustainable processes comes in, right? And of course, there are all kinds of definition, but there are also global challenge aspects like climate impacts. I talked about it. Of course, one, to understand, I use aerosol science, but I also want to remediate or tackle these. So one has to question. And if you look at the materials domain, we want to make advanced materials. They can help us overcome many challenges. Like if you look at solar photovoltaic materials, they are coming in a big way, but how many of us have them on our roofs? Expensive, maybe not the most sustainable way. So a lot of research needs to be done. We need to couple it to storage or battery systems, which are now, of course, also being used in automobiles. And then this CO2 issue, right? Can I design a catalyst? Can I design an adsorbent to not only capture, but also convert the CO2, or couple it with a petrochemical process system and do this? So those I would throw into the advanced materials bucket, but then there's a whole bunch of commodity materials. I just pick cement. We use cement or concrete for making these big structures all over, right? Is that the most sustainable? Could I have a review of the process of making it, or have certain additives which would suppress or reduce the carbon footprint? Agricultural products are very similar. So this is where we need to step up. And how do you do it? There are tools now being brought. Is the process holistically, environmentally desirable, right? And of course, it's known as a simple life cycle analysis. You can draw some boundaries and you address the issue of economy, society, environment all together. And then there are concepts of supply chain, circularity, and other important considerations. Some very nice references that I list at the bottom. And one can, of course, get into these and dive into detail. The carbon footprint, this is also now very much a standard thing people know. For example, in transportation or in energy production, electricity production, if I use fossil fuels, I have a large footprint, and you look at the total amount of CO2 emitted, but also commodity materials that I talked about have a large footprint. So can we do something about this as we go forward, right? So this is the thing that I'll use. And one slide I wanted to show, again, referring to my colleagues on the entire holistic carbon aspect that we study at the University of Miami, all the way from direct air capture. In some sense, desperation is setting in. You want to convert it. That's where the circularity comes in. You want to make products of value. You want sustainable fuels. We are familiar with it. You want to look at the right. You want to use sustainable precursors. So this is an overall process that one has to study. And there are individuals who pick simple products, right? Could be a consumer product that we use and begin to use these things. And on the right, I show you a flying vehicle. In Miami, it's a test bed. I also learned Dubai is another one where electric vehicles are going to now take off vertically and land vertically and fly in low altitude, right? So all kinds of things happening, but you have to keep this overall picture in mind and so forth. And I'll try to illustrate that. So I'm going to now focus on carbon products and just talk about carbon-based products, right? And some of these concepts, and of course I want to bring my aerosol science back. That's my field that's near and dear to me, and we'll talk about it a little bit. But before that, everyone drives a car or rides a car. We all see these tires, they're black in color. They have carbon black that is added to the rubber so that you don't have to change your tire every time you go to fill gas or petrol into your car. These are made from petrochemical wastes. Carbon black is indeed made from a waste. So it's not that we are trying to come up with new things, because these are also economical pathways to produce these. And this is an ingredient in all tires made by aerosol processes with a precursor or a feedstock that is a waste, right, of another petrochemical process. Of course, people are after tires being not the best, and even an electric vehicle, they point the finger with the braking and so forth. They're going to be sloughing off these carbonaceous particles. Can they be better? And someone might like a blue tire, a pink tire, a green tire. You can do all of that with other nanomaterials. But focusing on carbon, there are other carbon dots, quantum carbon dots, which have tremendous functionality for all kinds of applications, right? So like for drug delivery, for photodynamic therapy, for use in our television sets, organic LED televisions. So the ability to make this is great, and they're just being driven by the functionality. To be frank, it's not that they're looking at the overall sustainability. In fact, they're made by very much energy intensive and corrosive chemistries, because they just need the material for use. And to some degree, yes, the application drives it, but could we do better, right? So biomass precursors are a source of carbon. People are now beginning to use these. So just like the petrochemical waste for carbon black, can we use this to make carbon dots and so forth, right? So this is where the thinking has to come in. So I'm going to pick now as a case study in the remainder of the time, just talk about this precursor, lignin, which comes from plants. By the way, plants are used for many different things. People talk of bioethanol, but biorefineries, but also to make paper. And no matter what you do with the feedstock, which is the tree or plant material, the cellulosic components are taken up, but you end up with lignin, which is considered a waste byproduct. Probably good not to use the term waste, but just byproduct. And then, of course, you got to do something with this. They make nice fire logs. If I go up north in the United States, it's cold now, even now, and you can burn it in your fireplace and take care of it, right? But can we do better, right? So, of course, I add the paper industries. So lignin valorization by solvothermal and batch techniques is a tremendous pathway to make all kinds of materials, right? Lignin nanoparticles for agricultural applications as carriers of fertilizers or nutrients, composites for nanomedicine, and then composites with sulfur for supercapacitors, porous nanocarbon materials for also battery applications, and supercapacitors. So this is already being done because of the high value material, but limited property control, right? Still have to tweak these processes, many harsh chemicals used, and batch processing, which takes forever. So this is where I want to step in. Can I use an alternate, or using my knowledge, develop a process? So this is just a simple schematic. Lignin is a polymeric material, right? If I can choose or make it a water-soluble component, or even if I can make it in suspension and spray it out, nebulize it, and send it through a diffusion dryer, is nothing but a dryer, but then a furnace aerosol reactor, maybe I can make these materials in a single step, right? So a single step, and by controlling all those things I talked about, I can control the porosity and so forth. I didn't talk about these instruments. We also online hook up these instruments because the properties will be a function of size, and I want to measure these in real time, at least when I'm developing this process. So there is a chemical transformation. I'm not going to talk too much about the chemistry, but we have tons of data also using infrared spectroscopy or FTIR, but basically it's a polymer. You want to fragment it. You might want to form a char and then completely depolymerize it and get a carbonaceous product, right? If I want to make carbon nanoparticles. And then I got to keep track of all the other condensables that are produced or all the other products if the temperatures are such that I get a partial chemical transformation. It's a physical transformation because I talked about it. I'll just allude to in this talk that how do I go from a lignin particle to a carbon nanoparticle? Do I end up with carbon aggregates? Is sintering an issue? And so forth. And I'll refer to that later. So there are a whole bunch of input parameters. Again, this is aerosol reaction engineering. Just like chemical reaction engineering, you put all these things together and you can predict some of the characteristics downstream. So just to show you some examples, so let's start with a lignin droplet, and depending on, I run it at room temperature, 23 degrees Celsius, let's say, it's not going to decompose chemically, it's low temperature, but these particles, the lignin droplet will dry out. I might get a lignin nanoparticle depending on the concentration I start with. I can have collisional growth. Remember those collisional characteristic times. I will have collisional growth if the residence time, that little t is the residence time, is greater than the collisional characteristic time. If I start elevating the temperature, I begin to now promote chemical reaction, start breaking up these polymeric chains, and I can have then downstream condensation, collision, sintering, and so forth. I'm throwing sintering in because many of the practical reactors have big challenges with sintering taking place with these agglomerates and plugging up, right? So, and then of course I could go even higher and end up with carbonaceous particles. So this, and then you can collect these particles, and they all of course look pretty, but they have all subtle differences in the electron micrographs, also in addition to things like the surface area and so forth. Okay, so let's just pick on some results. I can vary the temperature. Now that I have a simple system, I know some of the important parameters. I already talked about temperature. Let's just change it. And I'm just here showing you the surface area of the resultant powder that is being produced at the exit. And that's a BET technique, which is a standard technique, gives you the surface area per unit mass. As the temperature goes up, you can see that the net surface area goes up. primarily because you're decomposing the lignin particle into smaller particles. You might be increasing porosity, and as the temperature shoots up beyond a certain point, there's a significant increase in the surface area. I can choose, let's say, and of course the goal here, depending on what application, I want a high surface area material, so I pick the largest temperature and vary the residence time. Now the dynamics takes place, like at low residence times, I won't have collisional growth and things like that, no sintering, but you also see that there's not sufficient time for the chemical reaction to take place. That's where the quantitative comparisons come in when I really want to explain this data. But the net is I can make high surface area carbon nanoparticles, because I got to keep in mind my application folks who want to use some of these particles. But simple studies like this in a laboratory system gives me these things. Now I want to say, okay, it's working. Can I scale it up? Can I have a continuous pyrolysis reactor? And so forth. This is where you really want to crank up those models I talked about. But there's a practical issue with sintering. When I want to increase the yield or the throughput, because of the higher concentrations, I have collisional growth, and they form agglomerates, and then they sinter, and they actually plug up these reactors, right? So we really need to understand and suppress that process, so that I can continuously run my pyrolysis reactor. And this is where I say, hey, nobody has studied simultaneous sintering and reaction, and then the student wants to develop a model, again, quickly showing you some of these parameters. And this is, again, a qualitative way. So I start with a distribution of lignin particles. When reaction takes place, I lose some of the constituents, so clearly the size decreases, right, because I'm decomposing my particles. But then when I collide them, they again shift to the right, the green size distribution. And then when I sinter it, I get some kind of shrinkage in the particle mobility size shown by that blue size distribution. And of course, I want to understand this very carefully so that I can use it. So I bring back my good old equation with the right terms. I won't go through it now. You've got some exposure to that. But in addition to this, I have a reaction term which I have to toss into this equation, right? So I need to study that. And I really want to study sintering. So you see what is sintering? It's shown at the bottom. Two particles collide, and then they slowly merge into a single particle, right? There's a driving force that tells me I want to become a spherical shape because it's the minimum area. But depending on the time, I will be in some intermediate state. Now, I can definitely not use a spherical assumption now. So let's just look at, so I track the volume of the particle, which is the size of the particle. And just to point out, so the first term increases the size or the volume by collisions. When two particles collide, the size will increase. When I have chemical decomposition, it's going to reduce the size. If I have some nucleation due to vapors, depending on the critical size, again, I'll tend to increase the size. And the last term is that condensational growth term. So we really account for all of this. Now, to solve this, I really need to track the surface area because the sintering is driven by the surface area. So I similarly have an equation for the surface area of the particle. Again, similar terms, but now I have a sintering term which tends to reduce the area towards a spherical shape, and I have all the other contributors. So these two take place simultaneously. I need to really understand the sintering constants, the decomposition rate. I don't even have expressions. So I need to do a set of experiments to pull these values out. So I go back to my laboratory scale system. And before that, I need a sintering model. It's not readily available for some of these species. So you see that I can form these agglomerate structures with a lot of neighboring particles, but most of them have a single neighbor or a second neighbor, right? So I'm going to forget the larger coordination number clusters, and that's of course an assumption because we need to do that. Then I bring in the concept of certain geometrical models, and when I have two, you can see that there are certain parameters, and again, I'm not going into great detail here, but I basically want to get expressions for each of those parameters as a function of time, and of course, simultaneously with reaction taking place. So I track the volume, the surface area, the primary particle size, the particle overlap, as I call it, and the number of primary particles, right? So it's now getting a little complex and a lot of detail, but as long as you're accounting for things, you can write down expressions, and you have to keep track of the number of primaries and so forth. So eventually you put all of this together. On the left-hand side, the reaction model, on the right-hand side, the sintering model, and we really need to determine some of these rate parameters, which are shown here, right? Because I need to plug them in. So there's no report in the literature. So I go back, I do very controlled experiments. Now, see how I'm using my tools. This is just the schematic of a differential mobility analyzer. I put it at the inlet so that I can take a single size, monodispersed size into my reactor. I don't want to play with that distribution. I can change the size. So at the inlet, I get a single size in, and then I measure at the outlet what happened to that single size, right? So this then allows me to, of course, look at the change in the size or the volume, and I plot out and get an Arrhenius type expression and can fit the reaction rate constant and so forth. I would want to change the size, which we do, and do this for a series of sizes to ensure that this is independent of particle size, which it turns out to be. If it turns out to be a function of particle size, there's a lot more head scratching to be done to ensure that we account for some of these things. So the ability to do very detailed experiments comes to forte here. Once I have the kinetic parameters, I do a similar experiment now with agglomerates. Now this would be a mobility equivalent size for the agglomerate, and then study if I wait enough time, it's going to become a single sphere, but I can measure the mobility size again. Prior to entry into this furnace reactor, I have a collision chamber so that I can create some of these agglomerates and so forth. And I plot the change in surface area with temperature. Again, I fit an expression to get the characteristic time and some of the Arrhenius parameters for sintering. So a very fundamental set of measurements which gives me this, and I'm just going to put it all together now. And I really want to apply this because an eventual chemical products person might want to make antioxidants or UV protectants. They want to know how they would run their reactor. So you can see that I can come up with this guide here, and the colors are just the progress of sintering. At low temperature, I don't have much sintering, right? That is known. It's a time temperature driven process. And for a UV protectant, I might want an agglomerate. For an antimicrobial, I want an agglomerate. So I don't want sintering to proceed significantly. So as I increase the temperature, I go into a sintered state, which means it's collapsing into a single sphere. At a given temperature, as I increase the time, I also move into a sintered state. So we put all this together, and you can see at the bottom, of course, I'm going to show you one result for a supercapacitor here, but depending on the application, the same reactor you could tune, and it all comes with the detailed knowledge of aerosol science and so forth. So negligible sintering, and those are actual pictures now, electron micrographs of particles, and you of course validate your detailed map and so forth. These carbon nanoparticles are tremendous for use in supercapacitors, and you want to compare it to the conventional materials used. And of course, you would now make a suspension and make a film, put it into a 3-electrode system to measure the capacitance, and these are all cyclic voltammetry, charge, discharge, and you see that you can get a rather high capacity which is maintained. The problem with supercapacitors, it degrades with time, but because of the well-prepared nanomaterials, you get a rather high specific capacitance, which sort of is sustained. So these are also a whole bunch of measurements that one would do to figure this out, right? So, and then you want to understand what really, why is the specific capacitance so high? You want to get the conditions. It's directly correlated to the specific surface area, which gives you some guidance. And then you want to compare to what is available in the literature. The key advantage of this is it's a continuous process and it's much shorter time scales, right? But people are using these batch and multi-step processes because of the demand for these materials, and the functionality is about the same or maybe slightly better, but you can see that the production time is significantly reduced. I want to take a full circle back and say, oops, what about life cycle analysis? While I'm cutting the production time, I'm getting a good material, really is this a sustainable pathway, right? Like questioning myself. Many times people now use the global warming potential as a metric. So we want to do this in a similar manner. I will draw system boundaries around my process because you have to start somewhere. It's basically an accounting process, and you have to account for all the mass and energy balances and estimate a global warming potential. So from my laboratory scale reactor, I now bring in a scaled up design, which would have realistic unit operations, right? And I also want to make sure, of course, I start putting values in. I want to recycle some of the thermal content of the exhaust gases, maybe through the heat exchanger, all kinds of things. And these are all optional pathways, and of course they have to be practical. So we come up with a system like this, and this is my boundary. In all these cases, I want to use lignin. Lignin itself has a negative carbon footprint or a global warming potential because it's coming from byproducts of biomass-driven processes, but then we want to study in detail, is this process really better? So I'm plotting now the global warming potential in terms of kilogram CO2 equivalent per kilogram of carbon nanoparticles produced, right? So you see the batch processes, the hydrothermal treatment, because of all kinds of activating agents, is significantly higher compared to, let's say, even a batch pyrolysis process without additives and so forth, right? And compared to our aerosol process, it sort of turns out to be one of the best in terms of being a single step, quick residence time turnaround, and so forth. And you do that for chemicals and for electricity. And then You could also say, I want to look at the global warming potential, but not in terms of a mass of material produced, but in terms of functionality, which is farads of capacitance, right? The specific capacitance. So here again, it's just now accounting and making these plots. You see that the aerosol process still wins out, again being obvious because of the lower residence times and well-designed processes. And this is now for a scaled-up comparison. You can take it a step further, right? So people are looking at using different kinds of carbon-based materials. Graphene oxide. Graphene is extremely high because it tends to collapse. The sheets collapse and you lose surface area, whereas graphene oxide, maybe you can retain some of it, and so forth. Activated carbon from coconut shell, another process. You don't have to just do this for lignin, but you want to now compare these different things. In fact, the coconut shell wins out over the lignin, and so forth. So you can use all of this to really guide your processes. So in summary, I'll pause here and answer any questions that you might have. This is a large volume, millions of tons per year product or byproduct. I can make wonderful materials all the way from highly porous carbons. I can incorporate sulfur into this carbon matrix and then use it for battery materials. Carbon silicon composites is another one, all kinds of applications, all enabled by a good understanding of the aerosol process. I didn't talk about much of the chemistry and so forth, but you can then put it to good use for a variety of applications. So with that, I'll pause. If there are any questions, these are the students and collaborators who helped in this particular project also, some of the collaborators, and I'll be happy to answer any questions. Thank you for listening.
We have time for questions.
Yes.
Yes, thank you very much for your interesting presentation. I'm a bit interested in one preparation detail. Mm-hmm. Could you go back to slide 26?
Oh, 26.
So my question, I can start with the question already, is dealing with the lignin.
Yes.
So the very, when we now see 26, in the very left, the very first step, looks very simple. You have lignin powder and then lignin solution and so on.
Yeah.
But as far as I know, the lignin, or I know the lignin is a highly cross-linked material, high molecular weight. And in order to get it in solution, you have to process it. And what you have in the end is lower molecular weight, is non-cross-linked, and it contains sulfonate groups.
Yes.
And this would be my question. Where is the sulfur then? In the end, in the porous carbon nanoparticles, do you still have the sulfonate ions or whatever?
So this is a very good point. I just picked a certain, lignin is of many different kinds, right? The polymeric structure with the unit, like I call it M here, could vary, right? And certain lignins are not even water soluble, as I just mentioned in passing. In that case, yeah, there is some pre-processing to be done. Like you want to maybe get it in a smaller size that you could spray it out and run some of these reactors. So this was a very controlled study, intentionally a certain, I can't remember the exact polymeric form of it, which is in some sense clean and also water soluble, right? But you can also take other forms of lignin and make them water soluble, as you're saying. If I do that, if I go all the way down, I'll have to consider that in some form as a penalty in my calculations, right? But more importantly, when I have other components like sulfur, and I'll give you another good example of something that's happening all over the United States now. I have to account for the sulfur. So these are pyrolysis reactors. So most likely the sulfur will remain with the carbon matrix, and I'm going to get a carbon sulfur composite, right? Now, depending on the application, I told you there's tremendous interest in carbon sulfur composites for battery applications. Maybe it's the first step in doing that. In fact, we ourselves have done it, but we have had to add another module where you add sulfur further on. So this is a very good question. This is very controlled in the laboratory, choosing a very specific type of lignin. Now, the example I want to give is another compound called PFAS. PFAS is a fluorinated polymeric carbon used for firefighting, used in your cooking vessels, and people have just spilled it all over. So in Florida, the entire soil in a large range is contaminated. So how do you take that out? And now people are just interested in destroying it. But instead of combusting it all the way, which is also difficult, and you end up with fluorinated compounds in the exhaust, can I convert it to a carbon fluorine composite in a pyrolysis type reactor? So these are all good points, but very controlled here and so forth. But have to,
Thank you.
The chemistry I didn't get into much.
Thank you. Very similar question. I was actually going to ask you the same, but okay, let's go a little bit further. So you don't have the sulfides lignin, you have the kraft lignin, kind of.
Yeah, right.
Softwood, hardwood, what is the better here? Because in terms of like the molecular weight, put it like that, people normally divide it into softwood and hardwood. Do you have any preference for that? Because it depends on the crop that each country is kind of like collecting.
Correct, correct. So you have to be very specific. So your question is, what is the
Best
desired?
source.
Right. Firstly, it's coming from a certain process, so you might not have much choice. And again, here in a lab, you could be easily sorted out, mainly for better understanding. But you have to account for these when you're scaling up and so forth. So the source of lignin, the type of lignin, these are all very important. Yeah.
So,
and depends where it's coming from.
Yeah, you
Right.
don't
Which
have too much
biomass
of source.
source?
I mean, the people in the pulp and paper industries, they're using the lignin to supply energy to the boilers.
Yes,
So
just burn it
you
back.
only have one chance when they are revamping this.
Yes.
So in any case, when you're producing this, I mean, the LCA is a tool, it's nice, it's relative, but you have 98% concentrate, like reduction of volume.
Yes.
That goes to CO2
Yes.
from lignin, so it doesn't count.
Right. So you're talking of the net material that is produced, the carbon.
Two things. The first one
Yes.
is it going to CO2 or is it going to CO at
Correct.
that temperatures?
Right. So yeah, you have to be cautious about that. So if you're running a pyrolysis reactor in nitrogen, most likely you're not going all the way to CO2, right? So you have to account for some of those aspects too in your system, right, when you're scaling it up. But in most cases, that is a single oxidation step, and you would then burn off the remainder in a large-scale reactor and so forth. They do that even for the batch systems.
Thank you. Thank you very much.
Yes?
Thank you. Thank you for your presentation. Since your carbon is porous, and the porosity or the pore size are important for certain applications, and the pore size can be a function of the residence time and the temperature. Can you model that?
Yes. In fact, we do. You didn't see much of that here because I was just playing with the size distribution as the parameter. So in addition to the size now, you will throw into your expression a porosity, which is a function of the particle size, right? And how do you model it? So you want to know the detailed decomposition, kinetics, and the structure of the lignin, which really there is good knowledge about it. You have to account for it. I'm not saying it's simple, but these are things that you would have to do. And some of it we drive empirically, because through the measurements we can establish the porosity, and we've done some of that, at least empirically, to improve understanding. But a complete model would be complex, but could be done. Right.
It depends on how it decarbonizes.
Correct. Right. And then the transport through the pores as they are forming and things like that. Right. So maybe you'll have to do a very uniform particle study, like I said, get everything to be a same size and then study the porosity evolution. Right? Yeah.
Yeah. Thank you.
Yeah.
It was a very nice talk, but my question is on slide 27. For example, if you go to the slide 27, here we talk about the nucleation, collision, and so on. But you also showed us that from lignin, you are able to make these carbon particles.
Yes.
And the size of the particles tends to vary. And the variation in the size, have you done the elemental analysis on these particles? Are they only carbon, or they constitute of the other hydrogen, nitrogen, or so on?
Yes, so very good question. I need to be beyond a certain temperature to ensure that it is a pure carbonaceous material, right? And we do the analysis to figure that out. So that's why you see I have two temperatures here in some sense. So at this temperature, it's sort of completely pyrolyzing all the way to carbon, whereas these are more mixed species and things like that, right? And you also have the reverse. At a slightly intermediate temperature, you might condense some of these vapor species back onto the structure, even if they might come out as per your kinetics evaluation, but then they recondense and you end up in the structure. But at a higher temperature, maybe they're getting knocked out completely. Right?
But if it is like a particle which is created at a very high temperature, like 1050 degrees Celsius in your case, that will not sinter at 700 degrees Celsius. Because it is already thermodynamically stable at that high temperature. So in your diagram, when you are talking about sintering process, that will be strongly dependent how the particle and at what temperature it is produced and what are the constituents. So sintering seems to be a bit complex scenario for me to understand how, because in your slide 9, you showed that two particles can collide and can sinter.
Correct.
So does my temperature reaches to those values by such a collision? And what is the driving force for sintering? So this creates a little bit challenge for me to understand.
Yes, so in some sense you're absolutely right. So what will a pure carbonaceous particle sinter, right? Obviously, if the temperature is high enough, would it reach that state in a pyrolysis reactor? Now, in full-scale systems, in batch systems, they observe this all the time, even while making carbonaceous. And it might be partially pyrolyzed with some of these condensables then, or these intermediate species, creating these to stick together and sinter. What we did in our sintering experiments were just sort of a single run through and track the surface area. But you're absolutely right. To get a detailed understanding of sintering, I need to couple the chemistry. And it is indeed a function of the chemistry, but we haven't really gone into that. Maybe a next step would have to do that. But it's a good point. Yeah.
Thank you. Thank you for the nice presentation. So in slide 31, you specified that the models or the model that you applied is based on the assumption of monodispersity, right? So I would like to ask if the polydispersity, because it could be like quite common that, for example, in combustion processes, let's say, for example, soot, this polydispersity could take place. So do this polydispersity could have any implication on your models?
Yeah. I mean, the complexity of solving it computationally increases, right? That's what I was trying to illustrate earlier on. Many of these property values then are a function of particle size, correct? And you have to then throw that into your equation and keep track of it. So the complexity numerically increases, but you do the monodispersity just to pull out the parameter values as a function of size, right? But that's a good point, and yeah, how complex can you go eventually, right?
Thank you.
Any more questions? Pratim, I have one. So have you played with reactors with different temperature zone along the axis so that you can play with the time scales and control different processes?
Yes. So what was the question? Sorry.
Have you tried reactors with different temperatures, time zones in series so that you can control the time scale and the different processes?
Right. We haven't, but you know, to completely close the thing, that's what you would do. So what we do is hold the temperature, change it one value at a time, and then repeat the experiment. So you're trying to say is, yeah, so let's say I say at low temperature, there's no sintering happening, the downstream do a high temperature sequentially. Yes, so we haven't done that other than repeating the full experiment. But that's a good point to show the transition, yeah.
Okay, if no further questions, please join me to thank Professor Pratim Biswas again.